In this second part of Lecture 2, we reach back to the oldest known mathematical problem, namely the Pythagorean triples, which is in the intersection between number theory and geometry. This problem is subject to a Babylonian clay tablet given by George Plimpton to the University of Columbia, known as Plimpton 322. It contains, as you can see on the screen, sophisticated integer solutions to the equation a squared plus b squared equals c squared. Plimpton 322 dates from around 1800 before Common Era, which means that this problem was known before Pythagoras, who lived around 500 before Common Era. It is obviously related to the famous Pythagorean theorem, which states that a squared plus b squared equals c squared holds in any right triangle with arms a, b, and hypotenuse c. I hope that you know that the converse holds as well. The Pythagorean triples inspired many great mathematicians and have been a source for many recent and beautiful development of the subject. But this is another story that might get us out of the scope of our lecture. Our aim here is to find all the Pythagorean triples, and the most famous of those is 3, 4, 5, and we can easily check that 3 squared plus 4 squared is equal to 5 squared. Here we get 9 plus 16 is equal to 25, and 25 is 5 squared. Another example is given by 11, 60, and 61, and we can actually check that 11 squared plus 60 squared equals 61 squared. We can verify that this holds by straight calculations, but there is another tricky way, which consists on saying that this equality is equivalent to this one, 11 squared equals 61 squared minus 60 squared. And here we say that this is equal to 61 minus 60 times 61 plus 60, which is equal to 1 times 121. And I hope you know that 11 squared is equal to 121. What we've done here is true, so is our first equality. Actually, there are infinitely many Pythagorean triples, and we can derive many of them in the following fashion. Indeed, you can multiply this equality here by 2 squared to get 2 squared times 3 squared plus 4 squared equals to 2 squared times 5 squared. This gives us actually 2 times 3 all squared plus 2 times 4 all squared equals to 10 squared, which gives us 6 squared plus 8 squared is 10 squared, and we can verify that this is actually true because this gives us 36 plus 64 is equal to 100, and we get that 6, 8, 10 is a new Pythagorean triple. We can do the same thing with 3 squared to get 3 squared times 3 squared plus 4 squared equals 3 squared times 5 squared, and we get 3 times 3 squared plus 3 times 4 squared equals to 15 squared, which gives us 9 squared plus 12 squared is 15 squared, which we can verify easily because 81 plus 144 is 225. So in this fashion, we can get infinitely many Pythagorean triples, and actually if x, y, and z is a Pythagorean triple, then for every k, integer k, kx, ky, and kz is a Pythagorean triple. However, we cannot obtain all the Pythagorean triples by multiplying a known Pythagorean triple by an integer k, because as we've seen here, 11, 60, and 61 cannot be derived from 3, 4, 5, because for instance, 11 is a prime number, it cannot be a multiple of 3 or a multiple of 4. We say that 3, 4, 5 is a primitive Pythagorean triple because in some sense it is the smallest among a family of Pythagorean triples that generates all of them. We can see here that 11, 60, and 61 is a primitive Pythagorean triple because 11 and 60 do not have a common divisor greater than 1. Thus we get the following definition. Let delta be a Pythagorean triple. We say that delta is a primitive Pythagorean triple if x and y have no common divisor greater than 1, or said in other terms, if the GCD of x and y equals 1. I remind you that GCD here refers to the greatest common divisor of x and y. A primitive Pythagorean triple generates infinitely many of them. Indeed, if x, y, and z is a primitive Pythagorean triple, then if we multiply this by an integer k, we get kx, ky, and kz, which is another Pythagorean triple, which is of course not primitive unless k is equal to plus or minus 1. I hope it is obvious for you now that primitive Pythagorean triples are the building blocks of all the Pythagorean triples. In other terms, in order to describe all the Pythagorean triples, it is sufficient to describe the primitive ones. It is time to get to the beating heart of our video. Take a deep breath, fasten your seatbelts because it's gonna be a bumpy ride. It is not very obvious how to find all the primitive Pythagorean triples. In what follows, we're going to investigate a very clever trick due to his excellence, Diophantus of Alexandria. Some of us might think that ancient mathematics are simple and naive, but we will see that this is wrong. Indeed, in his famous book Arithmetica, and in order to solve the Pythagorean triples, Diophantus came up with an incredible idea. Let us get back to our main equation, and let me remind you that we would like to solve the equation x squared plus y squared equals z squared for x, y, and z integers. We distinguish two cases. Case 1 is when z is equal to 0. This is actually simple and trivial. This implies that x squared plus y squared is equal to 0, and actually it implies that x and y are both 0. One can see this by the inequalities. X squared greater than 0, but it is lesser than x squared plus y squared, which is equal to 0. This means that x squared is 0, which implies that x is 0. This equation implies then that y is 0 too. Hence, when z is equal to 0, we get the trivial Pythagorean triple 0, 0, 0. The second case is when z is different from 0. In this case, we can divide both sides of the equation by z squared, which yields x over z all squared plus y over z all squared is equal to 1. Now how is this going to help us find all the primitive Pythagorean triples? Well, I hope you recognize here a geometric shape, which is the unit circle. This means that xyz is a primitive Pythagorean triples if and only if the point M of coordinates x over z and y over z, notice here that both of these coordinates are rational numbers, is a point of the unit circle which is of equation x squared plus y squared equals 1. Thus finding Pythagorean triples is equivalent to finding rational points which lie on the unit circle. Now that our original problem is transformed to a geometric problem, all we have to do is to locate rational points on the unit circle. Here where intervenes the tricky idea of Diophantus, the absolute genius. Here is his idea. First, notice that some rational points are easy to locate on the unit circle. For instance, A of coordinates -1, 0, the point here of coordinates 0, 1, this point here of coordinates 1, 0, and this fourth point of coordinates 0, -1. Here we choose to work with our point here of coordinates -1, 0, and notice if M is a point on the unit circle of rational coordinates, then the line here has slope t, which is equal to y over x plus 1, and this is a rational slope. Conversely, every line of rational slope t passing through -1, 0 has equation y equals t times x plus 1. Diophantus asserts then that a line passing through -1, 0 with rational slope t must intersect the unit circle in a second point with rational coordinates. We will show this fact by straight calculations and find the rational coordinates of this point here. Indeed, the intersection of the unit circle and the straight line of rational slope t has a system of equation y equals t times x plus 1 and x squared plus y squared equals 1. Said in another term, a point M of coordinates x and y lies on both the line and the unit circle if x and y verify these equations. Let me remind you that we do not suppose x and y are rational here, we suppose t rational, and we would like to show that x and y will be rational. By substituting the first equation in the second equation, one gets the following equation: x squared plus tx plus 1 all squared equals to 1, which is equivalent to x squared plus t squared x plus 1 all squared equals to 1. And let me remind you that t here is a known quantity and we're looking for x. So x is the unknown, and this is a quadratic equation in x. In order to solve a quadratic equation in x, we can use delta. But there is one tricky way to solve this without calculating delta. Actually, this equation is equivalent to x squared minus 1 plus t squared x plus 1 squared equals to 0, which is actually, by factoring x squared minus 1, is equivalent to x minus 1 x plus 1 plus t squared x plus 1 all squared equals to 0. And now there is a common factor here, which is x plus 1. So we factorize by x plus 1 to get x plus 1 factors x minus 1 plus t squared x plus 1 again equals to 0. This latter equation can be rewritten as x plus 1 factors 1 plus t squared x plus t squared minus 1 is equal to 0, which is equivalent actually to either x is equal to minus 1 or x is equal to 1 minus t squared over 1 plus t squared, which is non-zero. I hope you noticed that getting x equals minus 1 as a solution is natural because the first point of intersection between our circle and our line is of x coordinate minus 1. Thus, the x coordinate of our point M here is 1 minus t squared over 1 plus t squared, which is a rational number. To compute the y coordinate, we get back to this equation and write that this is equal to t 1 minus t squared over 1 plus t squared plus 1, which is equal to 2t after straight calculation divided by 1 plus t squared. So this is the y coordinate. Thus, all the rational points on the unit circle except minus 1, 0 are of the form 1 minus t squared divided by 1 plus t squared, 2t divided by 1 plus t squared. I claim that we're actually almost done. Let me go through all this again. First, we were looking for integer solutions of the equation x squared plus y squared equals z squared. And we said that this is equivalent to finding rational points on the unit circle. Now, with the idea of Diophantus, we found that they're all of this form here. Now, the fact that the second point of intersection of this line is of these coordinates gives us the equation 1 minus t squared over 1 plus t squared all squared plus 2t divided by 1 plus t squared all squared is equal to 1. This is actually equivalent to the fact that this point is on the unit circle. Now, the fact that t is rational can be written as t equals to a certain integer u divided by an integer v. If you substitute this here, we get 1 minus u over v all squared divided by 1 plus u over v squared all squared plus 2u over v divided by 1 plus u over v all squared again is equal to 1. If we multiply up and down here by v squared in both fractions, one gets v squared minus u squared over v squared plus u squared all squared plus 2uv divided by v squared plus u squared all squared is equal to 1. If we multiply now both sides of the equation by v squared plus u squared all squared, one gets v squared minus u squared all squared plus 2uv squared is equal to v squared plus u squared all squared. I know that you're probably lost here, but actually this is the magical formula that gives all the Pythagorean triples. Let's see how this works on an example. If we take, for instance, u equals 5 and v equals to 6, 1 gets 6 squared minus 5 squared all squared plus 2 times 5 times 6 all squared is equal to 6 squared plus 5 squared all squared. This gives us 36 minus 25, which is 11 squared, plus 2 times 5 times 6 all squared, which is 60 squared, equals to, here, 6 squared plus 5 squared all squared, which is 61 squared. Surprise! This is the triple that we used in the beginning of the video. To conclude, I would like to highlight that one can prove this formula algebraically easily by a straight calculation, but without our secret theory, it is a little bit hard to imagine. Lecture 2 Part 2 ends here, and we will investigate in Part 3 rational and integral points on a hyperbola. Thank you for listening.